Here's a nice little trick for calculating some simple line integrals. If you're careful, this trick can be used for any integral, but some of the bookkeeping gets a little bit difficult. And in those cases, often it's easier to just write out the fully parameterized line integral. Okay, so here's the situation. We're going to calculate the line integral of this vector field, capital F, from 0, 0 over to 1, 0. I should say along the line segment from 0, 0 to 1, 0. And then along the line segment from 1, 0 up to 1, 1. So this path starts at the origin, moves rightwards to 1, 1, to 1, 0, and then goes up to 1, 1, like that. Okay, we're actually going to do this integral in two pieces. First along the bottom part, which I'll call C1, and then along the second part, which I'll call C2. Okay, so our line integral is integral along the curve of f dot dr. And what we're going to do is, rather than using this fully parameterized way of writing the line integral, we're going to use this more differential way of expressing the line integral. So first let's go from 0, 0 to 1, 0. So 0, 0 to 1, 0. So on this part of the path from 0, 0 to 1, 0, x is, well, it's just x. X is going to go from 0 to 1, and y along this path is 0. And since y is 0, dy is also going to be 0. Right? If y is a constant, y isn't changing, and so dy is 0. So the part of this integral with dy in it, we don't even need to write it down because it's obviously 0. So let's just write down the part of the integral that has p and our x's in there. Okay, so dx, well, you know, if x is x, dx is dx. So this dx part, it's just dx. P is the x coordinate of our vector field right here. And we know what x and y is. X is x and y is 0 along this part of the path. So we can plug those values into here and we just get x. And our x values, right, we know our integral is with respect to x, so our bounds should be x values, and our x values are going from 0 to 1. So that integral is the part along the first path. Plus, now let's do the part of the integral from 1, 0 to 1, 1. This part of the path is vertical. Along this part of the path, x is the constant 1, and y is, well, y is just y. So dx, since x is a constant, dx is going to be 0, and dy is, well, it's just dy, since y is our independent variable. So we're going to do, for this part of the path, this time since dx is 0, the dx integral is obviously 0, and so we only need to worry about the integral with dy in it. So that's going to be the integral of q, and q is the second coordinate of our vector field. It has a bunch of x's and y's in it, but x is 1, y is y, so plug those all in. 1 squared is 1, minus 3 times y, and we're integrating dy. And since our variable for this integral is y, our bounds should be y values. Y is going from 0 to 1. And so we get this integral. Now both of these integrals, both the x integral there and the y integral here, both of them are pretty straightforward. You might even be able to do them without any work, but I'll write out a little bit. Integral of x with respect to x is 1/2 x squared plus, from 0 to 1, plus, now we'll do our y integral. This is y minus the integral of 3y is 3/2 y squared. This is from 0 to 1. Now we can just plug everything in. For this first one, we get 1/2 plus, and plug in 1 minus 3/2, and that all comes to 0. So this line integral is 0. The other line integrals on that handout from today you can evaluate in the same way. Actually, path C is a little bit trickier. But definitely path B you can evaluate in the same way, and it makes integrals along line segments very straightforward.